Thank you to all the organisers for organising the event and for inviting me to come and talk. It's my first talk in person in about 3 years, so I apologise if I'm a little bit out of practice or rusty. So today I want to talk about force balances. We've heard quite a bit already this morning and also a bit yesterday about force balances. So thank you to Johannes in particular for sort of laying some of the groundwork for me for my talk. So, well, outline, begin with an introduction, probably sensible. So I'm not going to go into great detail about some of the introductory stuff, but here's just a slide sort of showing the progression of geodynamo simulations. This is not comprehensive by any means. There's obviously plenty of simulations that have been done over the years that I've not included here, so apologies to all of you in the room who I have not cited here. But I've picked out a few, obviously the classic Blatzmeyer-Roberts reversing dynamo simulation, Ulli's parameter sweep from 1999, sort of mapping out different regimes you can get in these models. And then a couple of the more recent ones from Julien Albert and collaborators where Johannes mentioned they're following this sort of path in parameter space as they try and reduce the Ekman number. So this path in parameter space has also been alluded to by Emmanuel in his 2016 paper, where it's also called a distinguished limit. So you pick a particular, the idea is you push to lower E and PM, or if you prefer, either E and magnetic Ekman number, so you can think of it either way, by using some reducing parameter epsilon. So you pick a particular model where epsilon is 1, and then you reduce this epsilon towards 0, and there's some scaling which decides what you should pick, how you should move E and PM as you do so. And when we do such a distinguished limit or this path in parameter space, we should be doing it from a regime that's relevant to Earth's core. Here's regime diagrams. So these have appeared many times. This one I stole from I think Emmanuel's, or Keith and Emmanuel's book. So the key thing here is, of course, as E is lowered, dynamos are possible at lower PM. So each of these plots shows, so the top left is the largest Ekman number, bottom right is the smallest. And as you reduce the Ekman number, you can reduce the magnetic Prandtl number as you go and still retain dynamo action. So you can reduce, you can have dynamos at lower PM down here, for instance, than you can when you have a larger Ekman number. So there's a temptation, of course, because the Ekman number and the magnetic Prandtl number are both small in the Earth. There's a temptation to push them both down at the same time. But that's not necessarily the best approach. As we say in this distinguished limit, this path and parameter space, there should be some scaling to decide. So you don't want to keep pushing down. You don't want to be down here at the bottom all the time because you'll get not a very Earth-like dynamo. You want to be more up here somewhere, say, and then as you move down your parameters, you stay in this part of parameter space, for instance. So yeah, so this distinguished limit or this path in parameter space is a given the resources we have computationally is a better approach. And we've seen some of these plots before as well. So there's this idea of the weak and strong branches. This comes from work back in the 70s, in particular from David Fern and Paul Roberts. So the idea is that you, at the onset of convection, if your Alsacer number it gets large enough that it can actually aid the convection. So that's what this plot shows. As you increase the Alsacer number, the onset of convection will reduce. The Rayleigh number that you need to get convection going will be reduced. And then this leads into this idea of this strong and weak field branch, where if you so Lorentz had this same plot in her talk as well. When you onset with the dynamo action for a particular parameter regime, you will end up on this weak field branch, and then after a short period, you can jump onto this strong field branch. But actually, these two branches coexist at the same time. There's a bistability between the two branches. And then Emmanuel in 2016 found this in the dynamo simulations, where he found bistability between a weak field dynamo, and a strong field dynamo, and presented it in this sort of setup. So in particular, this is similar, but include to the previous plots, to this setup, where we've got weak field dynamos and fluctuating multipolar dynamos as you increase the Rayleigh number. But here you've got this additional strong field branch. So governing equations, I don't have much to say about them. I'm sure everyone in the room is familiar with such things. I've picked out the particular forces because I'm going to be talking about force balances. So inertia, the pressure gradient, Coriolis force, buoyancy, which we have a symbol A for Archimedean, Lorentz force, and viscous force. And then we have the temperature equation, induction equation, solenoidal conditions on U and B. So in particular, I'm thinking Boussinesq here, just appropriate for the geodynamo. So I'll use these when I'm talking about forces later on. I'll be using these letters to label each force. So force balances. Johannes did a good introduction on this for me. So I won't dwell too much, but there's all these different sort of balances we can talk about: geostrophic, magnetostrophic, the Mach balance, the Vac balance, etc. And these things they would certainly depend on the parameter regime, your input parameters. They will depend on the length scale that you're looking at. So if you're looking at small scales, the balance might be different to if you're looking at large scales. And in bodies such as the Earth, we expect, at least at some scales, the Mach balance to be important, because this gives rise, for instance, to torsional waves or magnetic Rossby waves. And these, given that we seem to find observations of these waves in the observational data, it's important that we run. Well, that tells us that the Mach balance must exist in Earth's core, for instance. So it's important that we run simulations that are in the right balance. So we want Mach balance to be appearing in our simulations. It's no good running simulations that don't have this balance. So then some previous investigations, again, there'll be more than these, and these are just some I've picked out because of the ones I've been looking at in particular recently. Brock and Jones, Krista's work, Rakesh's work, Nathaniel Schaefer, and some papers recently by Tobias Schweiger and collaborators, in particular Julien Aubert. They've been looking at these force balances. In these last couple of papers in particular, I've picked out some plots here. We've seen some of these plots already this week. So I picked out these are different regimes just to give you an idea. I'm going to use I'm going to be presenting plots like this later, and I've used the same color scale to sort of help us out a bit. But the idea here is that you can get different balances depending on the regime you're in. So up here, you've got this sort of geostrophic balance leading certainly at large scales, and then the Lorentz force becomes important at some scale and comes in and balances pressure later on. You've got a different one down here where it's geostrophic across the whole range of these are spherical harmonic degrees down here. So this is across the range of length scales, large scales at the left, small scales at the right. So I'll be presenting some plots from my own simulations that look a bit like this later on. So in particular, these balances, they typically include the pressure gradient in what sometimes is called this zeroth order balance. So at the top here, you've got this green curve, which is the pressure, and it's the largest thing across all length scales. Okay, it's the largest thing in all of these simulations. It's the largest thing in all of them, and then something balances it. So as I said before, Coriolis force, perhaps the Lorentz force, perhaps some other things depending on the exact regime you're in. But the key thing, if you only get one thing from this talk, the key thing I really want to get across in this talk is that well, I suppose two things. The gradient, the pressure gradient actually isn't important dynamically. It only enforces the solenoidal condition on U effectively. And there's a danger if given that all of the other forces have gradient parts to them, so, and I'll talk more about this mathematically shortly, but given that all of these forces can have gradient parts, they can all contribute to balancing the pressure gradient. So I would argue it's not right to only think about geostrophy, and we talk about geostrophy a lot, because at large scales, at least, the Coriolis force balances pressure, but actually what's important is the sum of the gradient parts of all of the forces balance the pressure gradient. So what we might like to do to get a better picture than looking at this, given that the gradient parts are not important dynamically, is to somehow eliminate the gradient parts of all of these forces and look at the non-gradient parts specifically. And that's so my title of my talk was an alternative look at force balances That's what I mean by an alternative look. We're going to look at the non-gradient parts. Well, we're going to eliminate the gradient parts from all of the forces. And so I will produce plots like this that don't have gradient parts in them. And just in case that's troubling to you immediately, as I mentioned this, because we're going to be removing, effectively the pressure gradient is going to be removed from the situation. Of course, we're used to doing this in simulations. We often take the curl of the equation, of the Navier-Stokes equation, that gives us a vorticity equation, the pressure gradient's gone. So it's a natural thing that we do anyway. The Taylor-Proudman theorem, Taylor-Proudman constraint, you only achieve by taking the curl of the balance between pressure gradient and Coriolis force anyway. So this is a normal thing. This thing doesn't care about the pressure. It just comes out as a natural balance between Coriolis and pressure when you take the curl. So a physical setup, the normal thing, we've got a spherical shell filled with electrical conducting fluid. It rotates, see about the vertical z-axis, rotation rate, omega, gravity acts radially inward, and we're assuming we've got constant values of the diffusion parameters and density. So effectively, this is a Boussinesq problem. So here's the governing equations that I actually use in the code. So these are now non-dimensionalized. In particular, this is what you might call the strong field setup, where you have this E over PM factor here. This is like a magnetic, well, this is the magnetic Ekman number that we've heard about. So I've mentioned that down here. You could use the magnetic Ekman number here instead of PM. So you need an Ekman number, you need a Rayleigh number. At least the way I've set it up, you need a Roberts number, which is PM over PR, and you can either use the magnetic Prandtl number or you can use a magnetic Ekman number, depending on what you prefer, I suppose. Okay, so in that equation, we have these forces I've highlighted before, so inertial force, pressure gradient, Coriolis force, Lorentz force, buoyancy force, and viscous force. And then you can talk a bit more about different balances you can get. So the classical one, of course, is the geostrophic balance. So you can have, if you've got nothing else going on, you've just got if you're just thinking about the pressure, balancing the Coriolis force, then that's obviously what it would look like. You take the curl and you get the Taylor-Proudman constraint straight out of that. And as I said before, this doesn't care about the pressure. You need something to balance this Coriolis force because it's got a gradient part. But actually, dynamically, when you get the Taylor-Proudman constraint, you take the curl, the pressure goes away, you don't care about it. So really, this is obviously the curl of, this comes out of the curl of the Coriolis force, but in particular, it's the non-gradient, or a way of representing the non-gradient part of the Coriolis force. You can go on and you can talk about, say, a quasi-geostrophic balance, which comes out a lot in these models. People talk about QG-MAC balance, where you've got this quasi-geostrophic balance at 0th order. Well, this is now the same balance as we had before, but possibly plus a bit of other stuff. Maybe the Lorentz force is somehow doing something, and the inertia is somehow doing something. Now you take the curl, and this will not be 0 anymore, but it may be approximately 0. So you'd expect this to be, so this one you'd expect to be definitely Z independent, the flow. This one you expect to be maybe a bit Z independent, but not perfectly so. And then you've got magnetostrophic balance. So in this case, you've got pressure balanced by Coriolis and Lorentz. You can take the curl here. This definitely now won't give you a Z independent flow because this is now a broken Taylor-Proudman constraint, because when you take the curl, you've got the curl of the Coriolis balanced by the curl of the Lorentz. And then question marks here because I see it come up in simulations, and I see it come up in my simulations, this balance where it's not magnetostrophic because the Coriolis force isn't involved. You've got a pressure Lorentz balance in some situations at some length scales. So, yeah, the length scale dependent force has been investigated previously. We've seen some plot. I've had some plots with Johannes talked a lot about Julien Aubert's work in particular on this. Well, Schweiger et al., including Julien Aubert's work on this. Schweiger et al., one of the things they do, as we've heard about before, they form this what we call a geostrophic Coriolis force. Okay, and this is formed by just taking the difference between the Coriolis force and the pressure. And I think this is dangerous because it assumes that only the Coriolis force has a gradient part to balance the pressure. Okay, so it's fine if you're happy that you're definitely geostrophic or almost geostrophic everywhere, but actually if in some regimes or at some length scales you're not geostrophic, then the gradient part of the Coriolis force won't be balancing the pressure gradient. It'll be balanced by some of the other forces as well. So I think a clearer picture is to directly eliminate these gradient parts. So obviously that kills the pressure gradient immediately, and it kills all of in an ordered sort of mathematical way. It kills all of the gradient parts of all of the forces. So you then are only left with the solenoidal parts, effectively, or some representation of the solenoidal parts of the forces, and that's what's important dynamically for the flow. So, in particular, you can write any of the forces as the curl of some vector potential plus the gradient of some scalar potential. So the idea is you can write this uniquely. If you then might basically want the idea is you eliminate this gradient part. So any of these forces can be written like this, and you want to eliminate the gradient part. Of course, the pressure gradient itself only has the gradient part. So in this work, what we're going to do is we're going to consider the forces, which is what people have considered before. We're going to consider their curls, and we're going to consider their projections onto the solenoidal part. So I'll talk a bit more about this momentarily. It's important to point out, obviously, this isn't a new idea. People have looked at projections before. In particular, David Hughes and Fausto Cattaneo have looked at projecting the force onto the solenoidal part in Cartesian geometry for simulations without inertia. So, but we're looking at it here in spherical simulations and trying to compare directly with Julien Aubert and Tobias Schweiger's work. So I don't want to go into too much detail here. There's enough maths probably for the audience, but as Johannes mentioned in his talk, you can basically write each force in terms of a radial, a spheroidal, and a toroidal part, and then you can expand these things in spherical harmonics nicely. And if you do so, then you end up with this. This is the thing that comes out. You can end up with an F subscript L, which basically gives you your forces as a function of spherical harmonic degree. And so that's what we do for each force. This involves integration over the radial domain, and it involves effectively integration over the azimuthal domain as well. So you can choose then whether to include boundary layers and such things. So you've got so here this integration can include a boundary layer or not, depending on whether you include it or not. So most of what I'm going to show you is going to take the viscous boundary layers out of the problem, out of the integration, because then we can look at the bulk, the balance and the bulk of the flow. But if I have time, I'll talk a little bit about what happens if you include the boundary layers. So as before, so we want to eliminate the gradient parts. So here's what each force will look like. We want to eliminate this gradient part. Simple and straightforward way to do this is to take the curl. So if you take the curl of this thing, it kills this gradient part, and you end up with basically the curl of A. So we could write this as, define this, and then just as the same method before as we did for the forces, we can go through exactly the same method. It's now, we're not using the force vector of each force, we're using the curl of the force vector for each force, but you can basically do the same decomposition, and you end up with something that I've termed CL, and now this is a length scale dependent curl of the forces. So that's one thing we can do, and we'll see plots of this. You can also calculate the projected forces. So here we are again. This is what our force looks like. We want to eliminate this gradient part. Now this is more complicated because basically it involves solving for phi. So the projected force is defined in this manner. So you find, the idea is you calculate phi, you take its gradient, and then you subtract that from F. So this is a bit like what they do when they find the ageostrophic Coriolis force. But of course, if finding the ageostrophic Coriolis force is assuming that the pressure gradient is exactly equal to the gradient part of the Coriolis force, which won't be the case. So here we're finding the gradient part of each force and removing it from the overall force. So again, well, to take some mathematics to calculate this, but effectively you can calculate this by taking the divergence of this thing of the force. That eliminates this curl part. And then so you've got the divergence is equal to the Laplacian of phi. You then, given that we know what F is because it's one of the forces in our simulation, we can then calculate phi by solving, effectively you have to then solve this ordinary differential equation. The complication here comes from the fact that this calculation for phi is not unique, and it's not unique because you've got to apply boundary conditions, and it's not obvious what boundary conditions you should use. So the boundary conditions that we've used are that d phi by dr should equal, so for each force, so there's one of these for each force, so the d phi by dr for the particular force you're looking at should be equal to the radial component of that force at the inner and outer boundaries. This is not unique, but it's mathematically convenient because it's quite simple boundary condition, and it's physically plausible. It's basically saying that the force that you're looking at can't push the fluid out of the boundaries. But as I say, this is not unique because basically here you can write, you can add any arbitrary harmonic field, any sort of, you can add here grad plus grad psi, for instance, by changing the boundary conditions, and it would still form a projection, but it would be a different projection. So the projections have the disadvantage that it's not a unique calculation, but it has the advantage that it's arguably more like the original force, because you're not taking an extra derivative with a curl. Right, and then just the highlights. So then, of course, if we do when we calculate this thing, we then can do the same method as before. So now we've got a different vector field. We just calculate PL. I've turned it this, and this is now a projection, a length scale dependent projection of the forces. So we will, I think maybe on the next slide I'd say this, yeah. So just some notes of where we've got to so far before I present the results. So we've got three representations of the forces as a function of L, spherical harmonic degree. We've got the traditional FL, which we've seen before in some plots earlier and in Johannes's talk. We can do CL, which is the curl. This will be a gradient-free expression. And we can do PL, which is the projection of the forces, which again is a gradient-free calculation. Just to mention again, we've got this ageostrophic Coriolis force. This, just to emphasize this point again, this assumes that only the gradient part of FC balances the pressure gradient. However, any force with the gradient part will contribute to this. So really, I would argue this only works, as I said before, where you've got geostrophic balance, or very, I don't know how to say it, very strong geostrophic balance across all length scales, where it really is the only thing that's going on, and that's not normal in simulations, and it's certainly not normal for Earth-like geodynamo simulations. And then just another note here, this is a slightly technical point. One of the problems with taking the curl is you increase it, you add an extra derivative because it's a derivative operator. And this can therefore boost small scales. So when you take an extra derivative, you often will unwillingly boost the small scales in your problem. So one way you can try and compensate for this, it's not perfect, but one way you can try and compensate for it is by introducing this factor here, L into L plus 1 to the power of minus a half, multiplied by CL. This is a partial uncurling of CL, if you like. It's effectively uncurling the angular parts of the derivative, where we can't uncurl the radial part. So we call this a compensated curl, and this is actually, so rather than actually plotting CL, I'm going to be plotting this thing. And this just means that it doesn't change the order the curves appear in, it doesn't change where their crossings are, but it just makes it makes the spectra look more like one would expect spectra to look like. It's a slightly technical point. You can ask me about it later if you wish. Okay, so right, the simulations. So we use this least spherical dynamo code. Thank you, Ashley, wherever you are. We use Busenesque, no slip, fixed temperature, electrically insulating boundary conditions. We run with a radius ratio that's like the Earth. We run at Ekman number 10 to the minus 4 for all of the simulations I'm going to show you here. Obviously, that's not very small. It's certainly not state-of-the-art small compared to what other people are achieving, but it's convenient for us because we're just trying to look at how these different representations are useful, and in particular, how you can find different regimes, or well, what the different regimes look like when you look at the different representations. PR is 1. This means that the Roberts number is just a magnetic Prandtl number. And here, I'm going to show you 4 different simulations. One's a hydro run, so it's hydrodynamic. I'll skip this one just for a second. One is a strong field dynamo. So this is on the strong field dynamo branch that Emmanuel talks about in his 2016 paper, and people have spoken about already today. Then I've got this other one, which I've called not strong field dynamo. I was debating what to call this. I could have called it a weak field dynamo, but it's not. We don't think it's on the weak field branch that we've shown earlier. So if we go back to that plot at the start where we had that weak field and strong field curve. This thing here, this run is likely not on the weak field branch. So I didn't want to call it a weak field dynamo because of that. But it's not. But the point is, it's different to this strong field one. So I've called it not strong field. A lack of a better explanation. If you've got any ideas what I should call it, then I'm open to hearing them. And then we've got a fluctuating multipolar run, just for we obviously know that that's another type of solution you can get, another regime you can get. So for completeness, that's included as well. Okay, there are various parameters here. That vertical line should be to the left of the magnetic Reynolds number, I've noticed. Now, these are all outputs, and obviously RM is an output as well. This is the Elsasser number. This is a modified Elsasser number. I don't really want to dwell on these things too much, but I'll put them there so people can see what the outputs are for the runs that I'm going to show you. We can talk about it later if you're interested. So the results outline. Okay, let's get on with it. So I want to consider the forces, curled forces, and projections, dynamo states. We can look at representations with and without boundary layers. I may not have time looking at the time. I think I probably won't have time to talk about boundary layers, but we, again, talk about it afterwards if interested. The aims, the two main aims are to examine the merits of using these different quantities, so the forces compared to the curls compared to the projections. And secondly, to identify key characteristics of the regimes that we can find in dynamo simulations when using CL and PL instead of FL. Right. Okay, so here we go. So I'm going to show you obviously a slide like this for each of the runs. On the left, we've got the traditional forces. In the middle, we've got the curled forces, and on the right, we've got the projected forces. So this is for the hydro run to begin with. So in particular, so if you look at the regular forces to begin with, we've got this geostrophic balance. You've got a green and blue curves up here, which is Coriolis and pressure. Okay, and then you've got other things coming in at sort of a first order buoyancy. I've included here this what they call this ageostrophic Coriolis force. This is this dashed blue line. And then it looks here like inertia and in particular this viscous force are very weak. Okay, so in particular the viscous force is negligible at all scales. It doesn't come in at all. Okay, but then when we remove the gradient parts, we look at CL or PL, what we find is we have a leading order balance between Coriolis and buoyancy. This is like a thermal wind balance, I guess, at large scales. And then there's a crossing later on, and you end up with a inertia viscous balance. So in particular, the viscous force comes into the balance here. And this is important because really it's got to, because we need some dissipation. So the viscous force has got to come into the balance somewhere, and that's completely lost in this representation. So the fact that the viscous force comes in here, and also in the projection, demonstrates that this, I would argue, is a more accurate picture of looking at the forces. We don't really care what the pressure gradient's doing. We don't care what the gradient part of any of the forces are doing, really. So by eliminating it, I think you get a better picture of what the actual balance that affects the dynamics is. In particular, this is not shown in FL because of the dominance of geostrophy and the QG assumption. These two plots, they kind of look similar, as we might expect. Effectively, they're both projections, but different to one another. So the ordering of the forces in particular is the same. The crossing points are sort of the same, but they're not identical. So, oh, I forgot about this slide. So this is just a quick comparison. This is all for this is comparing the Coriolis force for each of the different representations. So the solid blue curve is the force, just the Coriolis force. Which one's which? So the dashed blue curve is what they call the ageostrophic Coriolis. The dashed dotted one is the compensated curl, and the black one is the projection. So what you find is the projection and the curl do well. They match each other at sort of small scales. There's a bit of discrepancy at the larger scales, but as I said before, they're not the same thing, so you wouldn't expect them to be identical. But in particular, this ageostrophic Coriolis force does a really poor job over here. I mean, it becomes larger than the Coriolis force, which in some sense is sort of absurd. It does all right at large scales, poor at small scales. And if we go back one slide, we see the reason for that, of course, is up here, this is very geostrophic. So the ageostrophic force does a good job of representing the gradient-free part of the Coriolis force. But when you move over here, the inertia becomes important, and the Coriolis force becomes less important. Then the ageostrophic, the pressure gradient is not then balanced by the Coriolis force. It's partly balanced by the inertial force. So that's why this fails over here. So again, this is why I think it's important to just eliminate the gradient parts, and you get a more sensible representation. Okay, so this is now, we've put a magnetic field in now. This is a dynamo run. This is this not strong field dynamo. And again, so here you've got geostrophic balance across a range of scales, especially at the large scales. You've got a secondary balance between buoyancy and the ageostrophic Coriolis. The Lorentz force now comes in. Here it is in red, but it's not right up here in this anywhere in the primary balances. But then when you take the curl or the projections, you eliminate obviously the pressure gradient, and you end up with this picture or this picture. And here, so this is a run where this Lorentz force, this red curve, doesn't enter the primary balance. It's significant. It's a significant secondary force. It's more significant than inertia and viscous, but it doesn't enter the primary balance, and that's seen in the projection as well. So in some sense, this is quite similar. If I just nip back, this is quite similar to this run, except we've now got an extra red curve for the Lorentz force appearing in here somewhere. Okay, but otherwise it's kind of similar to the hydro run, but with an extra secondary force. And I think this is probably an intermediary regime between the classic weak field dynamo and the strong field branch. Okay, so then moving on to now, this is the strong field run. So this time we've got the Lorentz force is further up in the traditional forces plot, and there's a crossing. Johannes talked about these crossing points before between different forces and how they are important for maybe determining length scales for flows and energy injection and things like this. In particular, up here, the Lorentz force overtakes the Coriolis force and balances the pressure gradient on its own. And so this is why I said before, a pressure gradient versus pressure balancing Lorentz. It's not magnetostropic, it's something else, because the Coriolis force has dropped off. Now, if you look at the curls and the projections, you find, well, now you've got a triple balance. You've got this Mach balance. You can kind of see this here in the secondary balance here, okay? But it comes out really clearly here, and to a certain extent in the projection as well. You have this Mach balance, then you've got the buoyancy falls away, you've got a sort of an MC balance for a range of intermediary length scales, and then right down here, you end up with viscous and Lorentz force balancing each other. Again, we need viscosity to come into the balance somewhere for dissipation, and this is completely lost in the traditional forces. You don't see this; it just looks like magnetic. It looks like Lorentz force and pressure gradient, but of course, the pressure gradient is hiding the fact that the gradients aren't important, and what's dynamically important is removing the gradients and looking at this, and you can then see that the dissipation comes in here. Is there anything else I wanted to say? Yeah, and again, so this is why, so in particular for this dynamo run, it's dangerous looking at this ageostrophic Coriolis at length scales where the balance is not quasi-geostrophic. So again, the ageostrophic Coriolis does an okay job here. So the dashed blue line here is basically the same, it's going to be the same representation as this blue curve here or in here. But then later on, as the Coriolis force drops off, you see, it looks like here you've then got a magnetostropic balance, potentially, if you use the ageostrophic Coriolis. But really what this is saying is you've got a Mach balance, then an MC balance, and then a VM balance, I guess it is. So, to hurry up a little bit. And so then so we've looked at a lot of force balance plots there. I'm going to give you something that's actually the flow from the simulation. So these are plots of radial velocity for the three runs we've seen so far. So this is the hydro and the not strong field and the strong field. And so in particular, in the HD run, is strongly Z independent. And this is expected because it's geostrophic, and in particular, when you take the curl, you end up with du by dz is approximately 0. So it's very vertically aligned, as you'd expect. The not strong field dynamo run it's considerably Z independent. The magnetic field, remember that was the one where the Lorentz force is obviously present because it's a dynamo, but it's not entering the primary balance at any scale. So here you've got the magnetic field is not strong enough to break the geostrophy considerably, but it has an effect. So you can see, I mean, these two plots are similar, but there's some Z dependent motion in this one. But then if you go to the strong field dynamo run, it's significantly different. You've now got Z-dependent flow. I mean, this looks very different to these other two. And that's because now the Lorentz force is entering the primary balance. So when you take the curl, so in these two, if you take the curl, you would just get approximately du by z equals 0. In this one, you've now got the Lorentz force coming in as an extra primary balance force. So the curl of the Coriolis is now balanced by the curl of the Lorentz when you try and form the equivalent of the Taylor-Proudman theorem. And yeah, you can see this by the fact there's no Z, well, not no, but there's less Z-independent motion. There is some Z-independent motion, but that's because, of course, at local points, the Lorentz force might be weak. So you still have some areas of the domain where the Taylor-Proudman constraint holds, but broadly speaking, it's far less geostrophic or Z-independent compared to these two. Right. So final one to look at is this multipolar run. So again, traditional forces on the left. So this time, the inertia, which is in the purple curve here, has become more important, and the Lorentz force is weaker, what one might expect. Lauren showed something like this for the anelastic simulations yesterday. But again, the viscous force doesn't enter at any scale, if you look at this representation. And actually, apart from up here, the inertial force doesn't look like it's that big a deal, right? It's geostrophic, but then you take the curl or the projection, and the inertia is really important. It's there across all scales. And in fact, it becomes the primary balance up here at small scales. This is probably, the simulation is cut off here at resolution, obviously, but this looks like it's then ending up, it's going to be another VI balance here, viscous inertial balance. And you see the same thing in the projection, broadly speaking. And in this particular run, this is like the strong field dynamo run, except it represents an alternative way that the Coriolis dominance can be broken, an alternative way in which the Taylor-Proudman constraint can be broken. So in the strong field dynamo run, it's the Lorentz force doing that job of breaking the Z-independent flow, the Taylor-Proudman constraint. In this one, it's the inertia doing the same job. So I'll skip this because I'm running out of time, but there's some slides here on boundary layers. We can talk about that if people are interested. So some key conclusions. Sorry, I've got quite a few conclusions, especially because they're split over 2 pages. I'll try and just nip through them quickly. So the key things I want to say is that these 2 representations I feel are important, and I think they do a better job than the traditional FL because the gradient parts have been eliminated. It shows that the viscous forces are important in CL and PL. This is as expected for dissipation, but you don't see it in FL. So that's a failure, in particular, a failure of FL. I don't much like this ageostrophic Coriolis force. I think it's only sensible to use this where the 0 order balance is geostrophic. So at length scales where it's not, this doesn't really make sense. And in any case, I think it's much safer to use the curl or the projection anyway, because it eliminates the gradients of all forces. The pros and cons of each: the curl is unique. You can just calculate it. It's simple, it's unique, but it inflates sharp spatial gradients due to an extra derivative. And that's particularly an issue in the boundary layers, although I didn't get a chance to speak about it. The projection has no extra derivative, so it's in some sense the same order as the forces, but it's not unique because there's an arbitrary harmonic field which comes in by the choice of the boundary conditions. And then finally, some conclusions on the regimes that we've looked at in particular. So this not strong field dynamo regime and the strong field dynamo regime, they appear to be distinct. In particular, the Lorentz force only enters the primary balance in SD, in the strong field dynamo regime. And the not strong field dynamo regime is similar to the hydro case. These two, so this is the strong dipolar regime, this is the fluctuating multipolar regime. They exhibit different ways the primacy of the Coriolis force can be broken. Just mentioned that a minute ago. And I think particularly important from the point of view of this path parameter, path in parameter space, or this distinguished limit that people look at, is at some input parameters, for instance, these input parameters, as you vary RA, as you increase RA, there's a direct transfer from this not strong field dynamo regime where the Lorentz force is never in the balance. It goes directly to the multipolar regime. You never get this strong field dynamo, so you never get the Mach balance at some parameters. So I guess another takeaway message for people that are running simulations and trying to push Ekman number down is make sure you start in the correct regime that has a Mach balance in it. In particular, don't pick these ones, for instance, but there'll be other problems. So at PM equals 12, for instance, you definitely get a strong field dynamo, dipolar dynamo, which you can then reduce down from. And I'll stop there. Thank you.
Thank you very much. Very interesting addition to the last talk. So, that's what you wanted to say.
Nice talk. Two short questions.
Yes.
So the first one is, as you pointed out, when you do a Helmholtz decomposition, it's non-unique. It depends what boundary condition that you place at the outside, which can be a bit arbitrary. How sensitive are your results to that boundary condition you imposed, and can you physically motivate that boundary condition?
So the first question, unknown, because this is the only boundary condition I've tried. So obviously, each simulation requires, I run each of these things, and then when I calculate the projection, it's calculating as you, so you can time average, it's calculating as you do the projection, as you calculate the projection. So I'd have to run the simulation each time, arguably with a different boundary condition. It's doable, but I haven't investigated it from a time point of view. And then the second point, what was the second point you were asking? Sorry, Peter, remind me.
Can you physically motivate the...
Physically motivate. So I suppose from physically motivating it, so effectively what the boundary condition is saying is that each force cannot push the fluid out of the boundary. That's the condition we put on. Now that must be true across the summation of all the forces. You can't have the, if you sum all of the forces over, you can't have it must come to zero. So the best way I can physically argue it is that maybe each one does it separately as well. That's it's not physically plausible, but it's mathematically convenient, and it's not completely ridiculous. But okay. If you've got a better suggestion, I'd be happy to hear what you think the boundary condition should be.
I think the one you've chosen is sensible, because it matches the condition you put on the pressure when you invert del squared P equals.
Yes.
So second point about the chairman's willing to indulge me is I don't quite understand your problem with the decomposition on the Coriolis first, because if I introduce a vector potential for you, called A, solenoidal.
Yeah.
Then I can uniquely write down, I can do a Helmholtz decomposition very simply on Coriolis first. It's just Coriolis is 2 omega dot grad A, that's my solenoidal bit, minus grad 2A cross omega. That's the rotational bit. And to the extent that we're putting boundary conditions to one side, not worrying about that, then that's the job done. That's the decomposition done, which I'm guessing is what the earlier groups were doing when they talked about ageostrophic Coriolis first. So I don't quite get the point.
You're talking about the curl now, right? Or
no.
You're talking about the projection still.
I can do the Helmholtz decomposition without doing any curls, without doing any of the sort of mathematical apparatus that you had.
Right.
It's just I just expand curl A cross omega, and I get automatically a solenoidal bit and the Coriolis force.
Okay.
So I don't need any of the mathematical apparatus that you showed.
Okay. Well, maybe we can. I'm unaware, so maybe we can talk about it. Would that be the case for the other forces as well? I mean, you've mentioned the Coriolis force. Breaking your own rules.
Peter asked me to articulate more before, so I will try to articulate more. I can see that you can impose that the velocity is divergent free, but the Coriolis force obviously won't be divergent free, and so therefore you have to project it. Yes. Yes. Okay, I see what you mean. But then we have to worry about boundary conditions. I mean, but you will still have the ambiguity as to the projected Coriolis force will be non-unique up to an harmonic field. You still have the ambiguity. I mean, you have no boundary conditions on the projected Coriolis force. Therefore, you can add to it an arbitrary gradient harmonic field. depending on the boundary conditions. As you said, if you forget about the boundary conditions, yes. Well, that's a good discussion we should have later. But I think if you forget the boundary conditions, yes. If you have boundary conditions, there will be a harmonic field, and you can play with the boundary conditions on the projection force and change it. It's non-unique in that sense.
Yeah. Andy?
Thanks, Rob, for that very interesting approach. A question and a small comment. So you pointed out that the curl gives the extra gradient. Now I remember that Julien, if you were here, he was definitely vehemently opposed to taking the curl, and I don't really remember the reasons. I don't know if you're probably more aware of them than I am, so maybe you can.
Well, I think it's partly this. So, for instance, I've put some extra plots here at the end for convenience. So if you, so this is the plot I've shown you before for the hydro run. This is the compensated curl. This is the uncompensated curl. So in particular, it inflates, as you can see here, it inflates the small scales.
Yeah.
And I'd imagine that's what Julien would be grumpy about. But this, as I said before, this uncurling is only partial because we can only do it for the spherical parts. We can't do it for the radial derivative. So I'm not certain. I don't know if Emmanuel, if you know, but I'm not certain why you think it's a problem. I think it's not. Obviously, this representation is different to the forces, but and there's a compromise to be made. You know, that you have to partially uncurl it, and it's not very neat. It's not very nice in that sense. But I think it's more important to remove the gradient parts from each force than worrying about this, because as I said before, the ordering, as you can see here, the ordering of the forces doesn't change. The crossover points don't change. It's just you make the spectrum look a bit nicer if you compensate for it.
Right. The very quick comment, and people might differ in their opinions here, is that we've got this evolving language, and in fact, you seem to point out that you think Mach is different to magnetostrophic, and my view on the history of this is that Taylor wrote down a four-way balance, which included the buoyancy force, and then, to the best of my knowledge, Aitchison and Hyde in 1973 coined the nomenclature magnetostrophic. And so I think that four-way balance does not specifically need to be termed Mach, but that would be my view on what it's.
The nomenclature is something that I struggle with as well, because people seem to mean different things by the same term. So, yeah.
Is there any other question? Maybe I have a small point. Sure. You already alluded to it in this uncurling business. It also only takes care of the horizontal scales, but all these diagrams show forces versus L, so versus the horizontal scale, and a little bit, it worries me a little bit. What about radial scales?
Yeah.
Did you think about it? Is there any way to factor this in, or take
you could
care,
produce
or look at it
two-dimensional plots.
separately?
You could avoid doing the integration over radius and plot sort of L versus R, and
sure.
Schweiger and L do this in at least one of their papers. I just haven't got around to looking at that yet, but obviously it's something that we could do. You find in their simulations, you find that it does change with radius, don't you? So the balance can change sort of near the inner core compared to near the CMB, for instance. Something else that bothers me a little bit is the tangent cylinder and whether the balance is different within and in and
Yeah, that's a
and
different
outside.
question, whether
It is,
inside or outside tangent cylinder or different radii, it's different. But there's also the question of radial scales. If small radial scales behave differently from large radial scales. So
no, I haven't thought about that. No,
that's a difficult part.
No, fair enough. Yeah, I haven't thought about that. I've only thought about plotting this as a function of physical radius.
Okay.
But, yeah.
Okay, so let's thank Rob. Before we break for lunch.